Okay, one thing that I want to do is we haven't done any examples of this, but I would like to try an example of a Taylor series not centered at 0. All right. Remember, when it is centered at 0, it's called a Maclaurin series. So centered at 0 is the way we usually do it. And the series looks like this. F of x, when you write it as a series, this is the Taylor series. Well, it's called the Maclaurin, but it's also called the Taylor series. At 0 means you plug 0 into each derivative. Right? And you keep on adding them up with factorials in denominators. So this is the Taylor series centered at 0. Centered at 0 refers to the fact that each of those derivatives has 0 plugged into it. And the power of x is just a power of x. When you do centered at some other point, say a is just some other number. The way you do that one, I'm going to try to write a little bigger because I can see the screen is a little blurry. Instead of plugging 0 in everywhere, you plug a in everywhere, which is just this other number. And instead of powers of x, you do powers of x minus a. Like so. I'll write the third one. 1 over 3 factorial f, the third derivative at a, x minus a to the third. Right? This is a Taylor series centered at some other number a. Why would you want to do centered at some other number? Well, the question about where should I center the Taylor series from a practical point of view is mostly about, for whatever your function is, what number do you like to plug into your function? Now, usually plugging 0, so here I plug 0 every time, right? And for most functions, it's pretty easy to plug in 0. And so the Maclaurin series, or the series centered at 0, turns out to be the most easiest to compute and easiest to work with, because plugging in 0 to most functions is pretty easy to do. But for certain functions, you don't like to plug in 0. It's more convenient to plug some other number in to certain functions. For instance, this function, ln of x, you can't plug in 0. So it's not possible to do a series centered at 0 for ln of x, which is why we never talked about the series for that. Instead, we talked about the series for ln of x plus 1. That is possible because it's not. Then you can plug in 0. All right, but anyway, I'm saying this business about centered at other points is useful for functions where either you can't plug in 0 or for some reason it's very complicated to plug in 0. And instead, you choose some other number which you can plug in or which is easy to compute. So I just wanted to try one example. Now, this example, you don't have to center it at some other point, but you can if you want to. So let's find a series for sine x centered at some other value. And I'm going to say pi over 2. A series for sine of x centered at pi over 2. I hope you all remember. I'll do this sort of parenthetically in blue. Remember the series at 0, we talked about this last time. The series for sine x, it looks like x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5. It's odd powers with alternating signs. This was the series for sine of x centered at 0. We are about to see, if you do the series centered at some other point, it's going to look quite different. Let's do it then. The series centered at a equals pi over 2. Remember, the whole game for this, or the only thing that you really have to work at, is finding those constants. The constants in front of the various powers of x. And the way to do that is, f of x is sine of x. The first constant in the series is f, centered at 0. It's f of 0, but we're doing centered at pi over 2. So I'm going to do f of pi over 2. This is sine of pi over 2, which is 1. All right, remember, so I'm going to just refresh our memory. The graph of sine looks like this, where this is pi over 2, right? The sine of pi over 2 is 1. And just you'll see, because I'm about to take the derivative over and over again, we're going to have to talk about cosine also. The graph of cosine looks like this, right? And its value is 0 at pi over 2. So just that's going to come up right away. Let's do the first derivative to get the next coefficient in the series. The derivative is cosine x. So when I do f prime of pi over 2, I get cosine of pi over 2, which is 0, right? And we just keep on doing this as long as it takes for you to see a pattern. F double prime, somebody want to say what's the second derivative here? Negative sine of x, yeah. And so when I plug in f double prime of pi over 2, this would be negative sine of pi over 2, which is minus 1. All right, that's the third derivative. The fourth derivative, take the derivative of minus sine x, you get minus cosine x. The third, yeah, thank you. I skipped the third. The third, cosine of x, right? And so the third derivative at pi over 2 is minus cosine pi over 2. This is 0 again. And finally, when I do the fourth derivative, I will have made sort of a full cycle here, right? The fourth derivative of x, is going to be sine x again. And so the fourth derivative of pi over 2 is, again, 1. And then this pattern will repeat. So the pattern is 1, 0, minus 1, 0. And then it does that again. 1, 0, minus 1, 0, etc. All right. Great. I think we're ready then to write the series, right? It's these things in front of 1 over n factorial x to the power n. So my series then, it's sine of x equals, okay, first, I'll just write the formula for the Taylor series first of all. Using a equals pi over 2, it's going to be f of pi over 2 plus f prime of pi over 2 times x minus a, which is pi over 2, and then plus 1 over 2 factorial f double prime pi over 2 times x minus pi over 2 squared. I'll just go up to the next one here. 1 over 3 factorial f triple prime pi over 2 times x minus pi over 2 cubed, etc. All right, and we plug in. We already computed all those derivatives. They go, remember the pattern was 0, was it 0 first? No, it was 1 first. 1, then 0, then minus 1, then 0. So the first one is a 1. The next one is just all going to be 0 because my second coefficient is 0. So the second term there is going to be 0. And then plus 1 over 2 factorial. This was a minus 1 actually, so would you mind? I'm not going to put a plus. I'm going to put minus here, right? The next coefficient was a negative 1. So I'm going to put minus 1 over 2 factorial and then x minus pi over 2 squared. The next coefficient was a 0, so there is no power 3 term. The next term that does exist is the fourth one, right? The power 4 term. So the next term that does exist is 1 over 4 factorial, x minus 4, what? X minus pi over 2 to the 4. The next one would be the 6 with the negative. 1 over 6 factorial, x minus pi over 2 to the 6. All right, and this is our series centered at pi over 2. That's how we do it. Anybody got any thoughts about that? It's not really any different from centered at 0. You just have to, you just have to know how to do it. You plug in a different number than 0. All right, excellent. What I want to talk about mostly today, and this will be, I suppose, for the rest forever, right, is doing simple tricks with Taylor series. These simple tricks are actually similar to the one that you just did on the quiz, the second problem. The thing about if I already know a series for one thing, can I do simple modifications of that series to get series for other things? And the ones that we're going to be using today are going to be e to the x, sine x, and cosine x. So I hope you have these written down sort of in a list somewhere in your notes. I will refresh our memory. E to the x just has every term with a positive sign and those reciprocal factorials, right? And sine and cosine are like that, but they have only sort of every other term. The sine has the odd ones, the cosine has the even ones. And sine and cosine alternate their plus minus signs. So sine x is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus, etc. And then cosine gives you the even order terms, 1 minus, sorry, I'm writing here 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus, etc. All right, so those you should basically have memorized. I think on the final exam I'm going to give you this list, but hopefully you will have done these problems enough times that you will be able to remember those. I don't recall. It's not the 8th. It's like on a Tuesday of the week after. Yeah. Is that the 11th? It might be. It says on this the Monday. I'm going to look it up right now.
It has to be a Tuesday because the 13th is a Thursday. That's when we put the show.
Tuesday, May 11th, 8 a.m. Sorry about the time. I don't choose the times. Don't hate the player, hate the game. Yes, in this very room. Yeah, all of your final exams should be in the same, your normal classroom. Oh, really? All right. I don't know anything about that. Uh-huh. Okay, anyway. Memorize these. You don't really have to, but you're probably going to, just from doing the problems over and over again. Simple tricks is what I want to talk about. Easy sort of variations on these things. Let's try. Now, these ones, it's often kind of a pain to write out the answer as a summation. So usually I'm just going to say something like, write me the first 4 terms of whatever the series is. So let's try a simple one. Give me 4 terms of the series for x times sine of 2x. All right? And you're going to do this just like you did that one on the quiz. Hopefully you did that one on the quiz all right. I'm going to do sine of 2x by plugging 2x instead of x in the series for sine x. And then that whole thing, I'm just going to multiply everything by an extra x. So I would say, let me write out, first of all, well, it's x times, I'm going to do sine of 2x first. And this is obtained by plugging in 2x into the formula for sine x that you see at the top there. So it's going to be 2x, come on now, 2x minus 1 over 3 factorial 2x cubed plus 1 over 5 factorial 2x to the 5. I'm going to do one more just because I said write me 4 terms. So let's write 4 terms. Minus, the next one is minus 1 over 7 factorial 2x to the 7. And then dot, dot, dot. All right? And this is basically done, although I would like to write it as just constants or coefficients in front of powers of x. So I'm going to distribute that x on the outside over everything, first of all, and then it will become 2x squared minus 1 over 3 factorial. Now, to simplify this one, I'm going to do 2 cubed times x cubed. 2 cubed is 8, So this is times 8 times x. Now it was x cubed, but I'm also distributing x, so it's x to the 4 now, right? Is this confusing? Maybe just to simplify matters, just so that it's totally clear what I'm doing. I was trying to do sort of 2 steps at once. Let's just simplify the inside here first. Sorry. You can do both steps at once if you want. 1 over 3 factorial, 8x cubed, right? Then I have minus 1 over 5 factorial. 2 to the 5th is 32. So this is 32x to the 5 minus 1 over 7 factorial. The next power of 2 is 64, and then 128. So this is 128 x to the 7. All right. And finally, I distribute the x. This is my final answer. 2x squared minus 1 over 3 factorial times 8x to the 4 minus 1 over 5 factorial times 32x to the 6. Yeah, thank you. I messed that up. Plus 1 over 5 factorial. Minus 1 over 7 factorial times 128x to the 7. And that's my final answer. 4 terms. All right. I didn't say it before, but I could say it now. What's the radius of convergence here? Remember how you figure the radius of convergence. You think about what was the original radius of convergence. Now, all of these have the original radius of convergence is infinite. All right. So the original thing converges for all x. Now, I plugged 2x instead of x. Yeah, sure. This is my series. All right. What about radius of convergence? I plugged 2x instead of x. So the original one, the sign of x has the radius of convergence equals infinity. That is to say, it converges for every x. That means if I plug 2x, it still converges for every x, right? When the radius of convergence, say on the quiz, that one had radius of convergence equal 1. And so when you plug in 2x instead of x, you'd have to divide by 2, you get 1/2. But here, when it's infinite, you get infinity anyway. To the 8, yeah, sorry about that. I'm blowing it today. I hope you've already done your course evaluation survey. Then I can do whatever I want. It's all right. Sorry about that. That is x to the 8. Thank you for that. Anyway, since sine x has r, the radius of convergence is infinite, so sine of 2x also has r equal infinity. And so x times sine of 2x also has the same radius of convergence. So x sine 2x. All right. Basically, if you're doing any of these simple tricks with sine, cosine, or e to the x, the radius of convergence will still be infinite. The only time it might be different is if you're using that other one, the 1 over 1 minus x. That has a finite radius of convergence, but these ones are always infinite, so no big deal. All right, let's. I wanted to show you. So let's try another example. This is a much simpler example for the series. Let's try sine x over x. All right. So this one, rather than distributing an x, I'm going to factor this like that, and then distribute a 1 over x rather than distributing an x, which amounts to decreasing the power on x every time. All right. This we don't have to plug anything special in. This is easier than the previous one, but it's because I want to say something else about this after we do it. Anyway, the series for sine x is going to be x minus, same old thing, right? 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7 plus etc. And then I distribute that 1 over x through the whole thing, and we end up with 1 minus 1 over 3 factorial x squared plus 1 over 5 factorial x to the 4 minus 1 over 7 factorial x to the 6, and so on. All right? So this is a series for sine x over x. This is an easy example, but I wanted to use this as another sort of just to show you another way that the power series can be useful for something, we can use this to find a limit. Lim x goes to 0 of sine x over x. If you didn't use power series, this is not a very easy limit to do because the standard approach would be I just try to plug in x equals 0. I get sine of 0 over 0. So if we tried to plug in, it would say sine of 0 over 0, which is 0 over 0. All right, and this is no answer at all. Yes, you could use L'Hopital's rule in this scenario, and I would, like if this were a question on the test, I would assume that you would use L'Hopital's rule, because this is an easy example of using L'Hopital's rule. But if for some reason you didn't know L'Hopital's rule, or you didn't want to use L'Hopital's rule, you could also use the series to do this kind of thing. And there are some problems where the L'Hopital's rule is kind of a pain to do. Sometimes you have to do it like many times in a row. But it's easy to do this limit also using the series. So I will just say you could use L'Hopital's rule. It's a true fact, actually. There are, out in the world, many L'Hopital's rule haters. I mean real mathematicians, not like students who don't like doing it, but I mean like real mathematicians who think that L'Hopital's rule is somehow uncouth. And I've never really been part of that camp, but there are L'Hopital haters out there. They never want to use L'Hopital's rule for anything because they think it's somehow some sort of black magic or something. Anyway, you can use this series. Check it out. What happens if I try this limit as x goes to 0 of the series? So I go sine x over x, but that I write the series instead, and I get 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5. Sorry, I copied it wrong. It's x squared here is the first one. X to the 4 is the next one. Oh. All right, and what do you get when you take that limit? I am taking the limit as x goes to 0. So your first approach should be, let's just try to plug the number in. Plug in x equals 0. Do you actually get something? Yeah, you get 1 minus 0 plus 0 minus 0. Everything is 0 except for the 1. 1 is the answer, all right? In fact, if you have a really hard limit like this, it is a fact that if you want to take the limit as x goes to 0, all you need is the first term of the series. And that is, if you're finding series by various tricks, it's usually pretty easy to find. If all you care about is the first one, you don't hardly have to do anything to find that. So this is a cute approach to doing certain hard limits. Although often you can also use L'Hopital's rule. All right. Let's do some more interesting series examples. We can. Here's some types of tricks which we haven't done before. The one we did before was basically plugging stuff into another series and then distributing something. No big deal. Here's one. How about e to the x plus 2 cosine x? Can you find me? Let's say find the first 4 terms. All right. Our approach to do something like this is I'm going to add together the series for each of those two things, right? I can do the series for e to the x. I can do the series for 2 cosine of x. And then we add those series together. So I'm going to write the series for e to the x, which we remember this, 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And I'm just going to write the first 4 terms because that's all I need in my answer. You could write as many as you like, I suppose. And then what about 2 cosine x? Well, cosine x is what it is. You can look that up. I'm going to write that, but I'm going to multiply it by 2 throughout. So 2 cosine x is, remember, cosine x begins with a 1, and so the first term of 2 cosine x will be 2. The next term in cosine was minus 1 over 2 factorial x squared. So I'm going to put that here, minus 2 times 1 over 2 factorial x squared. The next term of cosine was plus 1 over 4 factorial x to the 4. But actually, that's going to be, I mean, it's past here. I guess I'll write it, but this is not going to appear in the answer. Because I tried to line these up because I'm about to add them together sort of vertically, right? We're going to add these up. You can even do like one of those, right? Add them. Add them. What do we end up with? E to the x plus 2 cosine x is, the constant term is 1 plus 2, which is 3. And then the x term is just x, because that one comes from e to the x, and there's nothing to add it up with from the cosine. The next one, e to the x has 1 over 2 factorial x squared, and then I am subtracting 2 times 1 over 2 factorial. These constants, if I may just simplify, this 1 over 2 factorial, of course, is 1/2. 2 times 1 over 2 factorial, that's just 1, right? So when I add those together, I got 1/2 and then a minus 1, which is negative 1/2. So this one ends up looking like that. It's very hard to say at this point what the pattern is, so I'm not even going to try to say what the pattern is for these things. The next one, the x cubed term comes from e to the x, and there's nothing to add it up with. So this is 1 over 3 factorial x cubed. Maybe I'll write 1 over 6 x cubed, just so that it looks nice and clean, right? I just have constants in front of powers of x. Those are the first 4 terms. So add the series together. You can do it. Any thoughts about that one? All right, I got another fancy trick. How about, yeah, this one is actually not convenient to try to write as a summation, just because, I mean, can you look at this and tell me what the pattern is for the constants? The answer is no, not really. I mean, there is a pattern, but it's not at all easy to say what the pattern is, right? So this is why I said, just find me the first 4 terms. I don't care about trying to write a general formula for it. It can be done. It's just well, what makes it hard is that the cosine is only relevant on every other term. So when you write out the formula, it's going to involve some weird things about, like it's a different formula for the even terms versus the odd terms. So it's not easy to write in a compact way as a summation. I'm not going to try and force it. Okay, here's another fancy trick. How about this? This one actually doesn't have anything to do with e to the x or sine and cosine. It's this. So I'm going to use this old one. I'll just do 4 terms as usual. But this one is not obvious at all how to fit that thing into this format that I'm looking for, 1 over 1 minus x. You know, like the one on the quiz, you could fairly easily, I hope you remembered how to do the one on the quiz, fairly easily squeeze it into this format of 1 over something, 1 over 1 minus something. But this one here, doesn't naturally fit that format. And you might think about factoring on the bottom and hopefully canceling something out. This is a good idea. If you factor on the bottom, you get x minus 3 and x plus 1, which unfortunately does not cancel with the numerator, and so that doesn't immediately help you out. We're going to do a fancier trick, and this is actually a nice little review trick. It turns out our old friend, the partial fractions, will work to complete this example. We have used the partial fractions before as a trick for doing the integral, although it is useful for other types of problems. So this problem doesn't involve integrals at all, but we can still do the partial fractions to help us do the series here. So I hope you all remember how to do the partial fractions. Remember the way this goes is I want it to look like this. The sum of these two things, and they are supposed to add up to 3x minus 5 over this. Y'all remember how to do partial fractions? On the left side, I'm going to add them together, make a common denominator. It'll say a times x plus 1 plus b times x minus 3. That's the numerator after you add the two fractions together. And then that has to equal the numerator on the other side, which is 3x minus 5. So this is how you would set it up. Anyone remember how to do this? What should we do next? Yeah, right. Let's. So we should rearrange the stuff on the left side. Gather together the things which are in front of x, which, like you said, is going to be a plus b, and then also gather together the constants. So I'm going to distribute first ax plus a, and then plus bx minus 3b. That's distributing. And then gather together the x stuff. It's a plus b in front of the x, and then also a minus 3b as a constant. And then we equate the like things. So on the left side, the coefficient on x is a plus b. That must equal the right side, the coefficient of x is 3. So a plus b is 3. And the constant, a minus 3b, equals the constant on the right, which is negative 5. And then we solve the system for a and b. You can do substitutions, or you can add and subtract equations if you like. In this example, if I subtract the second equation from the first one, the a's will cancel. The b's gives me b minus negative 3b will be 4b. And if I'm subtracting the first one minus the second one, it'll be 3 minus negative 5. It's 3 plus 5, which is 8. B is 2. If you don't like the adding and subtracting equations, you can do it some other way. There are many ways to solve a system like that. Anyway, b is 2, and then a plus b is 3, which means a must be 1, right? A plus 2 is 3, so a is 1. So this is the solution to that thing, which means my original thing, which was 3x minus 5 over that stuff, x squared, I got it written on my paper here, minus 2x minus 3. This apparently equals, a equals 1, so it's 1 over x minus 3 plus 2 over x plus 1. All right, we did the partial fractions. The whole point of doing all of that was just so that I could write this instead like those two fractions added together. Now, when you're doing the integral, you do each integral and you get the, two natural logs, basically. In this case, we're not doing the integral. We are trying to find the series. So for each of these, each one use this thing, 1 over 1 minus x, right? So I'm gonna write this in a more convenient format so that it looks like 1 over 1 minus x. The second one, I would say, is a little easier to handle in terms of that. You can just pull the 2 out of the numerator, and then x plus 1, I think of that as 1 plus x, which is 1 minus negative x, right? That's how you would rearrange that second one there. What about the first one, 1 over x minus 3? Well, you could pull a minus sign out, and then it would say 1 over 3 minus x. I would really like it to be a 1 minus x in the denominator. Anybody remember how we do that? How do we correct that 3 there? Yeah, factor 1/3 out of this whole fraction. So pulling 3 out of the denominator, if you like, it will look like this. Minus 1/3, 1 over 1 minus x over 3. I divided the 3 out of that whole fraction. And now each of those we make a series out of. So maybe I'll try and write them separately here. Minus 1/3 times, here, I'll write the whole thing, 1 over 1 minus x over 3. When I write this as a series, I get 1 plus x over 3 plus x over 3 squared plus x over 3 cubed, right? This is that geometric series. And let's do all the distributing and all that so that we can easily add. Remember, I'm going to add these two answers together. So doing all the distributing on the front, I get negative 1/3. Next, x over 3 times another negative 1/3 will be minus x over 9, right? Next, x over 3 is being squared. That's going to be 1/9 x squared times an additional 1/3. Will be minus 1 over 27 x squared. This one's not so hard to say what the pattern is. The next will be the next power of 3, x cubed. So this is the series for that half of it. And then to this I will add, the other thing was 2, 1 over 1 minus negative x. So this one, I'm going to have a 2 out front, and then 1 plus minus x plus minus x squared plus minus x cubed. This is 2 minus 2x plus 2x squared minus 2x cubed. All right? We alternate the signs and distribute the 2 everywhere. And finally, we can add them up, right? So I'm going to add this guy plus this guy, right? And you just add them term by term, and some of the numbers are going to be nasty here. So our final series, I'll just write the original form again. We've like transformed this thing so many times that I forgot what it looked like when it started. 3x minus 5 over x squared minus 2x minus 3. Okay, this equals adding them up term by term. So the constant from the top one is negative 1/3 plus the constant from the second one is 2. So it's negative 1/3. 2 minus 1/3. 2 is 6/3. Take away 1, it's 5/3, isn't it? That's the constant. Next, the coefficient on x. From the first one, I get negative 1/9. From the second one, I get negative 2. Would you mind if I just write negative 1/9 minus 2? Whatever that is, that's the coefficient on x. I don't care to try and simplify all these fractions. The x squared, I get negative 1/27 and positive 2 from the next one. So I'm going to say negative 1/27 plus 2 x squared. And then finally, the x cubed, I got 1 over 81 and 2, and they're both negative. So this is going to be minus 1 over 81 minus 2 x cubed. That's how we do it. All right. This is kind of a long-winded, but we did partial fractions, and then some simple tricks, and then add the series together. It really works. All right, I got one more. I actually had 2 more examples until the end of all things. We only have time to do one of them, though. We'll just do that. We'll fill in that last one next time. One more example. So the past two examples that we've done have been adding together two series, which you can do. We can also multiply. Now, this is a little trickier, although it's not so bad. Let's find, again, the first four terms of, let's try 2 plus 3x times e to the x. All right. So how do you do it? You do the series for e to the x, which you just have memorized, and then you multiply that by 2 plus 3x, which sounds simple. I mean, it's not so hard, but you'll see a little bit of subtlety here. 1 plus x plus 1 over 2 factorial x squared. Again, I'm going to write three terms here. Four terms, I mean. All right. Now, how do we multiply? How you multiply is, really, you got to distribute everything. So when I multiply this, it's kind of like doing the FOIL, only there are infinitely many things in the second part. This sounds scary. It's not so bad. How you do it is, you go through first, multiply everything by 2, right? Now, I'm not going to write infinitely many of them. I'm just going to write the first four of them. But this is how you would do it. You would go through and multiply everything by 2. And then also go through and multiply everything by 3x. Right? And then add all of that together. So let's see if we can do it. First of all, multiplying everything through by 2 gives me 2, first of all. That's 2 times 1. And then I have 2 times x. 2x. And then I have 2 times 1 over 2 factorial x squared. I'll just write exactly that. Then I get 2 times 1 over 3 factorial x cubed, etc. I only care about the first four because I'm about to add these together, and only the first four are going to be relevant. Next, I multiply through everything by 3x. I'm going to say, I'll just start this on the next line. Plus, maybe I'll sort of put parentheses around that. That's one thing with the dot, dot, dot. It actually goes on forever, but since all we care about is the beginning of it, we don't have to care about the rest of it. And then the second part, I multiply through everything by 3x. I get 3x plus. The next one, 3x times x is 3x squared. The next one, 3 times 1 over 2 factorial x cubed. The next one, 3 times 1 over 3 factorial x to the 4, like that. And then for my final answer, we add them up. And it turns out actually that last one that I wrote there is not going to appear in my answer because it's actually past the first four terms. If you write the first four terms of the answer, it begins with 2 was a constant, which had no other constant to add it up with from the second part. But then as far as the x's go, I have 2x from the first one, 3x from the second one. They add up and give me 5x. Next term, I have 2 times 1 over 2 factorial. Actually, 2 factorial equals 2, and so that kind of canceled. It's just x squared from the first one. And the second one has 3x squared. So this adds up and gives me 4x squared. This is another case where it's pretty difficult to say what the pattern is at the end. So we're not going to try. The last one that I'm going to write, because it's going to be the fourth one, it's 2 times 1 over 3 factorial x cubed, and then 3 times 1 over 2 factorial x cubed. And I don't know if you can simplify that in any reasonable way. I'll just say 2 times 1/6 plus 3 times 1/2, right? That's what that is. 2/3, no, 1/3 plus 3/2, I guess, whatever that is. I don't care. Plus, etc. All right, and this is the series for that. So the trick here was multiply them. All right. You know, I think we got time to squeeze in that last one. Are there questions about this one? All right, we might as well do it now. Let's do it. Power through. Rally. You got to rally. I had some. Do people still say that? My friends in college, They want to go out drinking all night. They get tired, and then they're like, "Oh man, I want to go home." And then one bro is like, "No man, you gotta rally. You gotta rally." Kind of my goal in life is to never rally. I'm not interested in rallying. I want to go to bed. No, sometimes you gotta rally. Although trying to stay up all night drinking is not my scene really. Dividing, that's the last thing. You gotta rally. I'm into rallying for this. Dividing, this is harder, but you can still do it. E to the x divided by x minus 1. All right? How do we divide? I'm going to do the long division. Check it out. Now, x minus 1, I'm going to write as this denominator. You'll see immediately why. It's better in this example to write it like this, negative 1 plus x. Negative 1 plus x divided into the series for e to the x is 1 plus x plus 1/2 x squared. It's 1 over 2 factorial, but that's 1/2, right? Just for this, I'm going to write 1/6 x cubed. 1 over 3 factorial is 1/6. All right? And we divide. I wrote the first 4 there because I'm going to divide in, and I want to do the long division for enough terms so that I get 4 terms in the answer. This is why I rearranged the polynomial out here, which I'm dividing by. It's because you want to see, when you write these polynomials, you should start with the constant, and then the x, and then the x squared. And you should do that for both of them so that they line up nicely in the long division. Anyway, how you do this, I look at this thing on the front here, and I ask myself, what do I got to multiply this to make it match that? And the answer is negative 1. I have to multiply by the constant negative 1. So that's my first term in the division up here, minus 1. I hope you remember your long division. Now you multiply that negative 1 times the thing which you are dividing, and it makes 1 minus x down there, right? That step was I multiply here times here, and I write it down there, all right? Then you subtract. The 1's cancel, as they should, and the x's gives me x minus negative x. That's 2x here, all right? And then I pull down my next term. So I have 2x plus 1/2 x squared. And I repeat the process. So next is I try to think about what do I need to multiply right here to match that. Negative 1, and I'm trying to match it with 2x. What should I multiply by? Negative 2x is the answer, yeah. Negative 2x. And copy that down. So now I multiply negative 2x here times this thing over here, and I write it down there. We get positive 2x on the front, and then minus 2x squared, right? And I put the line there, and I subtract. The 2x's cancel, as they should. The x squared gives me 1/2. Minus negative 2 is 1/2 plus 2, which is 2.5. I'll write 5/2. All right. We've got to do 2 more steps of this. Unfortunately, as you continue, the fractions will get weirder and weirder. This is usually what happens, and it's hard to make up the example in a way such that that doesn't happen. What's next? What should go up top next? Yeah, sorry, I forgot to bring down this guy, right? Up top should go negative 5/2 because I'm trying to make this, remember, match with this. Just the number there, or better be some x's. Yeah, negative 5/2 x squared. Great. Multiply that down, it gives me 5/2 x squared minus 5/2 x cubed. Subtract. We get whatever negative 1's the 5/2 x squareds cancel. The x cubes is going to be 1/6 plus 5/2. As sixths, 5/2 would be 15/6. Here I have 1/6 plus 15/6 is, I believe, 17/6. I bet you didn't think you were going to see that number today. 17/6 x cubed. And so my final term in the series here, I'm going to have to put minus 17/6 x cubed up there, all right? And then we can just stop. I mean, there's no sense in trying to multiply through again. Whatever the next term is, I don't care. This is my answer. Finding the series by dividing. It works. All right, and I think that'll do it. Thank you all for your continued participation and attention. Thank you, I will say, in the words of Joe Biden, closing off his speech. Did you all hear the last thing he said? He said the usual, like, God bless you all, God bless the United States of America. And then he said, and thank you for your patience. Such a kind, gentle soul, isn't he? Thank you for your patience. So I'll see you on Tuesday. We'll talk about the test. Have a good weekend.